Good afternoon, Putala. Anon. Hello.
Good afternoon, sir.
Okay, very good. Yeah. So this is an animation of gas molecules, but in a very uh, how to say. This is not at the actual speed. This is over 1,000 times slower speeds. Yeah. These gas molecules. So even molecules, whether we breathe, gas molecules, whether in the wind, or even gas molecules in a tube of a tire, or in a balloon, or even gas molecules in your gas cylinder. So naturally, they are not silent. Yeah, naturally, they are not silent. Yeah. So here you can see a huge randomness. That is one of the reason for the even for the entropy. So you see the randomness here. Even in this one, you can see the solids. Solids, they also vibrating. Yeah, not that much of movement, but it's vibrating. They are itself. Can be rotational, can be translational. Okay, but vibration is there in lattice form of whatever the atoms and the molecules. Right one. Don't worry about the temperatures mentioned. I just want to show you. Liquid molecules move further distances compared to the solid molecules, of course. And gas molecules are more violent, more violent. Now, somehow, gas, liquid, and solid states, the molecules and atoms, all are violent, all are vibrating, all are in motion somehow. In motion. So this is the nature of this. Okay, this is the nature of this. So it's okay. We just accept only. Yeah, we just accept only this situation. So this is in further slow state. You can say this. Yeah. So just be patient and have some thoughts about this. Yes, I'm going to add a text for this. Yeah. Please be patient for a while. I'm going to add a text for this. Yes. In this animation, you are saying you have seen the speed, what it says, okay? The speed, what it says, the atoms have a certain average speed, okay? The atoms have a certain, so this is, let's say this is considered the uh, helium atoms. So here, of course, the atoms have a certain average speed. Average speed, we can configure for all the atoms average speed. Here in the animations, slowed down 2 trillion fold from room temperature. Yeah. So you imagine 2 trillion fold slow down this. Yeah. So imagine the speed, if it is 2 trillion times this, it is unimaginable, and also it is, you cannot visualize it. It's not possible because equipments are not that strong. That is what the scientists, the researchers say. So these atoms are that much violent. Okay, so the average speed also, they are quite high. Okay, that is for your information. So even here, even in this animation, this is just at very slow speeds. At very slow speeds. So imagine at very slow speeds. So imagine in our body, also made of molecules and all the cells, tissues, uh, then the organs and systems, and even the our, even in the brains, yeah, brain also consider organs, and also the cardiac systems and all made of molecules, if you think in biology ways. So imagine all are vibrating, all are moving like that, because that's the nature. So imagine even the changes are so fast, the molecules, the movements and all. So in this way, our body is really something like, you imagine all the cells are like this, but we don't feel this. Yeah, that is the beauty of that. Yeah, we don't feel, but it's always like this. Yeah. It's always like this. Each and every cell, even in the hair, fingers, nails. So this vibration is there. Yeah. So nothing there as even as physical permanence. It's nothing. You know that in maybe, I think, over 100 days, all our cells are replaced. I think in over 100 days, all our cells completely replaced. They are maybe replacing cycles somehow. Uh, so there is a certain time in numbers, I think within 100 days. Yeah, or maybe in 2 weeks' time, I cannot remember. All the cells are replaced with new ones. All the cells. Yeah. So that's why always we are new, even though we are getting old. Somehow we are living with the memory. That's why we have something like we feel the history and all, but when it comes to the presence, we have a presence because this is quite changing. Even our thoughts are more faster than this, maybe unbelievable. So this is how the life of the creatures is, including humans. So anyway, even we are at this state, we are learning the subjects also. thermodynamics and all the subjects. So this is the situation. Anyway, back to thermodynamics. So today we are going to look into something. Yeah. So this is the background preparation for this. This is the background preparation. I hope you can hear very well. So if you don't hear, please, yeah, if you don't hear, you cannot comment even. I hope you can hear me very well. So there is an area called kinetic theory in physics and chemistry. They are really working on this in kinetic theories. They are really working on this. Yeah. But we are not here to learn the kinetic theories. They developed this very well. And somehow we are using that knowledge here. Maybe only a very little amount, that's all right. Yeah, that's all right. Not that big ways, but it is very important to feel this. That is very important for us, and that is good enough. So I'm going to add a bit by bit. And today my computer looks typing uh, no much issues. Last time we can see so many messages are coming. The temperature, yeah, this is what the scientist says. The temperature of an ideal monoatomic gas means that gas is a single atom gas. We only have helium like that. Yeah. The temperature of an ideal monoatomic, ideal means uh, there may not be any change in the, how to say, the magnitudes of the velocities, means no. Yeah, anyway, later we will discuss what the ideal gas means. But here uh, we will, yeah, just take it as the ideal monoatomic means the single atom gas. Yeah, later we have to learn what ideal gas means. So this is a background for that as well. So the temperature of an ideal monoatomic gas is proportional to the average kinetic energy of its atom. Yeah. So there is an average speed possible for that kind of a lump of atoms. Yeah. So average speed, there are also the atoms has some unit masses. So there is an average kinetic energy. So the temperature is proportional to average kinetic energy. So kinetic energy means the violency, the energy due to the motions. You know kinetic energy. If the mass is m and the speed, sorry, the velocity is v, kinetic energy is half mv squared. I think you know that. Kinetic energy. Okay. Kinetic energy is you know half times mass times velocity to the power 2. Okay, I will put v to the power 2. Okay, v squared. So that's how the kinetic energy, you know from your school educations. Yeah. So this is the kinetic energy term, half mv squared. So these are part of experimental based. Yeah. So half mv squared is the kinetic energy. So here average kinetic energy of its atoms. Okay. So it the average kinetic energy of the atoms proportional to the temperature means you can see when the temperature is very high, which means these molecules are more violent. That's why molecules are more violent, means higher temperature. Yeah, that's why even if you see high temperature, let's say steam, okay, steam, high temperature means, yeah, we feel it's a temperature, but it is really more violent H2O molecules. Steam means more violent H2O molecules. If you touch the steam, what happens? You get burn injuries. The reason is these atoms of steam, more violent atoms, uh, when hit the skin or your hand, then the molecules in the skin become energized and somehow becomes energized, and even these steam atoms may be trying to penetrate. As a result, your skin get damage or injuries. We call it burning injuries because of the high temperature. Okay, because of the high temperature. Even sometimes low temperatures. Even if your skin subjected to too low temperatures, you have some cold burns. Let's say if your skin subjected to, let's say, minus 50 all of a sudden. So in your skin system, a patch subjected to minus 50, molecules immediately become more silent. Then it will be something like separate from the skin system. So there can be some, uh, we call it a damage or a cold burn. Also possible. That's why in a system, if you, let's say, in a system, let's say in the skin system in your hand, if you heat up a patch, there will be a damage. Even if you freeze a patch, there will be a damage. And that's how the molecular motions, the violence, the impact is that severe. Okay? Yeah. So we can think about this. So the temperature proportional to average kinetic energy. Okay, temperature proportional to average kinetic energy. So that's why even the vehicle tire in the noon times, roads are very hot. And when you are traveling, maybe when you are driving hundreds and hundreds of miles, your tire become very hot. And when the tire hot means the inside the tire, the air molecules, or whatever, if it is nitrogen gas, maybe gas molecules inside the tire becomes more violent. High temperature means more kinetic energy. So then the pressure becomes very high because this violent, more violent molecules hitting the tire skin inside, it is more intense, and some cases even there can be tire blasts because tire cannot withstand that impact of molecules. Not only tire blasts, even you heard about the gas cylinder blasts. made of metal, so perfectly done. But sometimes if the gas molecules are very violent, and if it's so intense, even the metal can be ruptured, yeah, in very simple ways. Yeah, that's how the violence. So this is not to talk about the violence, but to learn about the internal energy. Okay, what internal energy means? Even in H equals U plus PV, you have noticed that internal energy. If I take the enthalpy definitions, okay, even in the enthalpy definition, you may have noticed that H is U plus PV, and today we need to talk about U. Okay, actually we should talk about U bit earlier, but that is straightforward. So this is just a clarification of what uh, internal energy or U means. Yeah. I hope you can see the slides. I hope you can see the slides. So today, so first effort is to understand here this U. What is this U? Internal energy U. So we have to understand maybe to understand this. Yeah. So here, what internal energy means. So that is what we are going to understand. Okay. Systems internal energy. Any system, maybe the gas trapped in a tire. Okay, gas pressurized in a tire, gas in a cylinder, or the air we are breathing. Yeah, will have this internal energy. Okay, internal energy. The system's internal energy. And this system's internal energy system's internal energy really reflects here. Yeah. So you already know the system's internal energy. The energy here you are seeing is the energy of the system's internal energy. So you are seeing the moving molecules. This moving molecules within this system, each and every molecule has an energy because of its motion. Okay. For these molecules are really moving, translational, and the straight moving in a straight line, hit something, change the direction, again moving in the straight line, change the direction after hitting. Then if not hit, it's running at a straight line. We call it translational. At the same time, these molecules can be spinning. We call it rotational. Spinning also, it's a movement. So this translational and rotational energies. Yeah, this translational and rotational energies combined. Those energy because of the motion or the movement of these molecules. That is what we call kinetic energy. and that energy is the internal energy of this, especially when it comes to ideal gases. If there are interactions or links or bonds with the molecules, then there are additional components, the bond energy for the internal energy, but here for the ideal gases, it is simply the kinetic energy. So let me add a text here. Okay, let me add a text here for the internal energy. I'm going to add a text for you. The internal energy. Okay. We need to read this together. Okay. All right. Very big fonts. Yes. Try to read this. The internal energy of a system can be understood by examining the simplest possible system. A system means that can be even the gas within the tube of a tire, or even the steam within the kettle or a boiler, or even can be uh, any system, maybe like the fired gas within the piston cylinder system in an engine, whatever. So let's say to understand, let's look into an ideal gas. Okay. Later we will learn what ideal gas means. Anyway, in ideal gas, because the particles in an ideal gas do not interact. Interact means either attraction or repulsions. So in a gas, we would see ideal gas has no interactions, no attractions, no repulsions. Ideal, ideal, because in real gas there are attractions, there are repulsions, gas molecules. But here in the ideal gas, we would see no attractions. Even two molecules can be very closer with no interactions. But in real case, two molecules, examples hydrogen, cannot be separated. Hydrogen maintains as H2, okay? No separate atoms, okay? So ideal gas has no potential energy, means no attractions, no repulsions. That's what it mentioned as the potential energy. So later we will learn more about this. Then the internal energy of an ideal gas is therefore the sum of the kinetic energies of the particles in the gas. So it's the kinetic energies of the particles in the gas. Okay. So if you go back to this, so kinetic energies of the particles in the gas, the total, that is what we call the internal energy of this gas system. We call it system because this has a boundary. So within the boundary limits, we are considering this and we are using the word system. Otherwise, we have to separate words for this gas. Maybe gas, how to say, gas container, whatever. The easiest way is to use the word system. Gas in a box, gas in an enclosure. So we don't need anything. There is a boundary. Within the boundary, the gas is there. So we call this system. So it's for the simplest usage. We are using the word system. So that's for the convenience. Yeah. Okay. That's for the convenience. System has a boundary. That's it. So within the boundary, all the matter within the boundary, we call it, that's the system. Okay. So that's how we refer the word system in thermodynamics for the easy wordings, easy conversations. Yeah, we use this. So here the total kinetic energy of this non-interactive atoms or molecules in this gas phase. The total kinetic energy is the total internal energy of the system. And this internal energy, we call it kinetic energy. And the kinetic energy is proportional to the temperature. See, the temperature of an ideal monoatomic gas is proportional to the average kinetic energy. So the kinetic energy, high, temperature, high. So finally, this kinetic energy related to internal energy. So then, when the total is the internal energy for the ideal gases, so the internal energy is proportional to the temperature. Higher temperature, higher internal energy. Okay. Higher temperature, higher internal energy. So please get this uh, clarified. Okay. Please get this clarified, Putala. Okay. Yeah. That is very good. So internal energy of a system, okay, for ideal gas, the internal energy of the system, I will put here, the internal energy of the system let's say for unit mass, maybe for the unit mass, and let's say U is 3 by 2 times RT. Okay, is 3 by 2 times RT, and I believe you know the R, the ideal gas constant. Okay, later we will learn about this. Even in PV equals MRT, you can see the specific gas constant and all. Here the ideal gas constant, you may have the special units for this. Okay, you may have the special units for this, and temperature is in Kelvin. So this gas constant is in joules per mole per Kelvin. Okay, so that one, and this, what R means. So yes, R. Okay, R is this. R is this, and your internal energy is 2 by U is 3 by 2 R. So per mole here, okay, per unit, as here in number of, here in per mole. So we will see what mole means later when we look into the gas laws. Okay, today we are not going to discuss the gas laws, but you can see internal energy is the reflection of the temperature for ideal gas. It's a reflection of temperatures, and also previous it says the temperature of, let's say, an ideal monoatomic gas. So let me take this even out for your convenience. Of gas is proportional to the average kinetic energy of its atoms. Okay, so I put in this way for your convenience. Okay, so now when the internal energy word comes to your mind, okay, so when the internal energy word comes to your mind, okay, when the internal energy word comes to your mind, what is at your fingertips? Fingertips. Cannot look for the books internally. So it's a familiar word. It should be the familiar word to you. What should be in your fingertips? Okay. The best is to have this visualization and tell yourself that it's the kinetic energy or the energy of the molecular motion of the molecules in that system. Plus, if there are molecular interactions like attractions, repulsion, those potential energies also will be counted. Okay, but generally you can say it's mainly the kinetic energy. Okay, kinetic energy, and it's also proportional to the temperature. Okay, for ideal gases, so you can, it's not necessary to remember this, but it's okay to have a simple opinion. So let me take this out. Let me take the other statement also out, and I will put this inwards. So this is in your mind. The temperature of gas is proportional to the average kinetic energy or the kinetic energy of atoms. You know that. So when it comes to internal energy, yes, you got it. The internal energy of an ideal gas, therefore, is the kinetic energies of the particles in the gas. So that's what this picture refers. Refer to this picture. The fingertips is this picture. Okay, the animation. The animation. You get this animation, and there can be translational and rotational motions. Okay. So when the internal energy word comes to mind, what is at your fingertips is this. Sum of kinetic energy, so energy due to the motion. Okay, energy due to the motion. Or I would say energy due to the motion. To the motion. Okay, to the molecular motion. Motion. Simple like that. Okay, simple like that. Because this familiarity is important when we deal with this parts. Okay, energy due to the molecular motions. Translational means moving in straight lines. Even heat, after heating, again it moves in straight lines. That's how the ideal gases. So it's okay for you to think in that way. Because most of the molecules can have ideal gas conditions at substantial temperatures and also at lower pressures. Okay, so approximately let's say 90% close. Okay, other than that, you have to look into for the internal energy. You have to look into the kinetic plus the other energy interactions. We call it potential energy, molecule to molecule attraction. Okay. So now you have little bit understanding of this. And whenever you need to get the values for the kinetic energy, you have to refer to data. Okay, that's the other point. Okay, that's the other point. So if you need values for internal energy, it's a good word we are using because we cannot think always about the molecular kinetic energies. So all the kinetic energies and the potential energies together, whatever, we call it internal energy. Okay. If you need values for internal energy, refer data. Okay. Maybe tables, example. Refer data tables. That's the only way. Okay. Refer to data tables. Refer data tables. That is the only way. Example, if you need to look into the internal energy of water or steam, you have to look into steam tables. You have to look into steam tables. No other choices. You have to look into the steam tables. Okay, you have to look into the steam tables. That's the only way. That's the only way. Example, if you take the Rogers and Mayhew, so let me take it for you. Rogers and Mayhew. Yes, here you can see the U values, UF, UG. See, means the liquid, the internal energies, gas, internal energies. Of course, when it comes to gas, your internal energy levels are much more higher compared to liquid. Yeah, over 10 folds, even 20 folds higher, because the gas molecules are more violent or more energized or having more kinetic energies and less potential energies. So let me put this on the slide just as an example. Yes, this much would be enough. So we'll go to this previous one. So I will have the table here for you. Okay, I will have the table here. Keep in mind, for liquid and gas, yes. So the liquid here is 2 trillion times slower. Gas one, left hand side, is 2 trillion times slower. So by right, this is more faster. Anyway, liquid also moving, the particles here also moving. So you can see somehow this UF line here. The fourth column is for the liquid. Okay. So take one more here to not to get too confused. Yeah, now you can see the blue and red color here. The gases are more violent. Okay, gases are more violent. You can see it. So let me take this out. Looks better. Okay, then gas. So here you can see the UF column and the UG column. The liquid, slower, gases move fast. So you can see even it's quite fast. You cannot recognize the motion. So that's how it should be. Okay, good. So you have basically some idea about internal energy more than the word internal energy. So you know how to take the internal energy values when it comes to the steam and water. So you can get it from the steam tables, or even there would be some formulas. So any special gas types, maybe nitrogen, hydrogen, ammonia, or whatever the refrigerant, you can find data as tables or as equations or as correlations. Correlations means you have several sets of expressions. By using that expressions, you can derive internal energies, or sometimes even as graphs. I hope you can understand this. Okay, what internal energy means. Yeah. So this is quite important to have this familiar wordings, what internal energy means. At least you can explain this. Yeah. At least you can explain this. So now in the enthalpy expression, should be quite okay for you. You know what is U now. Okay, plus PV. Okay, U plus PV is H. So you have some better understanding of U. Okay, and let me look into the steam table again. You can see in the second column temperature. See, the higher the temperature, down the column you can see temperature is rising. U value is rising, and the gas value, Ug value is rising more and more. That's why. So temperature reflects the kinetic energies, mostly for ideal gases. But anyway, temperature has a very good connection with kinetic energy. So higher the temperature, this internal energies, you can see it is increasing, means it becomes more violent. That's why when you boil water, even before start boiling, you can hear the noise. Even before boiling, during the heating up of water, you can hear the noise. That is the molecular motion. Okay, and your kinetic energy values are increasing because of the heat. That reflects as the increasing of temperature, and also it makes the increasing of the internal energy. Okay, and also of course for the gases, the gas phase of this means steam. Higher the temperatures, you can see higher the internal energy. So of course, since H is U plus PV, you can see H values are also increasing. Okay, H values are also increasing, especially for the gases. Okay, for liquid, PV has no much change because V is quite smaller, that's why. So you can see how the temperature reflection on the internal energy of liquid, internal energy of gas, and enthalpy of liquid and enthalpy of gas, and even on the entropies. Okay, even on the entropies. Yeah. So you have noticed this. So higher the temperature, entropy is getting reduced. So we will discuss this also afterward. But delta S equals delta Q, delta S. So we have calculated the S value somehow as HFG by T as SFG. We have calculated. Let us see why entropy is dropping. We will see why entropy is dropping. It is quite reasonable. Right? It's quite reasonable why entropy is dropping. because the higher the temperatures, higher the pressures, unavailability of thermal energy for useful work is less. That's why entropy becoming lesser and lesser when the temperature is rising. Okay? More energy is available for useful work for high temperature. Even for the power generation, you have to look for higher pressures and higher, even superheated. Yeah, higher pressures and superheated. That's why you see for the high temperatures, yeah, and pressures, your entropy is dropping. Means more energy is available for useful work. That's why. So this table is justified, and you have learned the term internal energy. And also you have already learned about enthalpy. And also you have some very basic, very practical idea about entropies. Okay, good. I hope you can understand this very well. And today I'm going to continue this further. And this way, okay, this way. Let's say now you have a very good basic background for thermodynamics. You have a very good basic background for thermodynamics. So now I'm going to draw a schematic of a thermodynamic system. Schematic means of a thermodynamic system. As long as if you draw the boundary of the system, the schematic of the thermodynamic system is done. The reason is within the boundary you are identifying the space within there, the gas, liquid, or even two-phase. We are analyzing that. Okay, we are analyzing that. So this can be the schematic of the thermodynamic system. No big deal. Okay, this could be a schematic of a thermodynamic system. But here to you just looks like a square. So we have to really add some wordings here. Let's say if you add some wordings here, yeah, definitely you have to add thermodynamic systems. Thermodynamic system. The very first thing for this is it has a boundary. That's it. It has a boundary. So outside the boundary, it's the surrounding. Within the boundary, it's a system. Okay. And there are two types of thermodynamic systems, not to say two, all are same. All are same. System is just a system, that's all. Yeah. So now we are going to evaluate the work and energy interactions. Okay. Work and energy interactions. Work, energy, and matter interactions within the systems. Okay, you have a very good subject flow here. Okay, work, energy, and matter interactions of thermodynamic systems. Okay, work, energy, and matter. So here, energy means we refer mainly the thermal energy. Okay, means the heat. Okay, heat. Energy means heat. Okay, let's say heat is, let's say Q. Okay, Q. Work W. W. And energy. So energy I can use even heat energy and internal energy. Internal energy and even heat energy anyways, since heat is separate, I will put here U and yes, I will put just U. Okay, since we have heat, I just put the it as Q. And matter. Matter is M, mass. Okay, let's see. Yes, energy here internal. I just put U or even internal U, and I can use the term capital E for the others, whatever E. Okay, energy is E, internal energy is U. I hope you can understand. So here thermodynamic system, I would say it is U here. You have a mass, capital M, or even small m will do. So mass is here. So there can be heat as well. Okay. So I'm drawing here the heat. Heat. Yes, it's okay, I draw. Heat. Let's say red color. Okay. With an arrow towards the system because we are adding heat. Okay, we are adding heat here. Okay. And it is Q. Okay. Q. And you work W. So I will get similar size also towards this. Towards this. This is work. Somehow I will just change only the color to black. Okay. W. Only the brackets. Okay. So what happens? This U. What happens? When you have W and Q, what happens? So you cannot simply write U. You have initial U and you have the final U. Okay, so there is a change of the internal energy because you are adding work and also you are adding some heat. Okay, you are adding some heat, so there should be some internal energy change. So U1 change to U2. Okay, so M may be the same. Let's say M, no change here. No change. Possible? No change. Okay, no change. So you have Q. So that's it. You know the system, you know the internal energy, so U1 has changed to U2. So your energy balance, okay? Your energy balance you can write, okay? Your energy balance. What's the energy balance? It's quite simple. You no need to memorize anything. Energy balance. That is what we call the first law of thermodynamics. We have learned this. This is quite easy for you. Energy balance. So what's the energy balance? So this Q can be Q net. The net heat, because you add Q, and also there may be energy, heat, thermal energy going out from the system. So we have the Q net. Net energy is 2 words. Also there can be W net. Okay, so Q net, you have Q net, energy balance, Q net, together with W net. Equals what? U1 change to U2. Okay, U1 change to U2. Oh, we would say this is change. We can use the word, not the word, the symbol delta U. Okay, you got delta U. So delta U is U2 minus U1. Give me a second, Buddha. Yeah, we are back again. Okay, delta U is U2 minus U1. Okay, equals delta U equals U2 minus U1. So this is quite obvious. Okay, this is quite obvious because energy cannot be created, also cannot be destroyed. So energy should be there, whatever. So for the system, initially there is an energy of U1. So the addition of W net work, also when work goes to the system, it turns into internal energy because work transferred generally to the molecular kinetic levels or the kinetic energy of the molecules. Yeah, that's why. Heat, of course, once go to the system, it's added to the molecules kinetic energy. So W net plus Q net is the rising of the internal energy. So this is the first law. For this system, okay, first law for this system.
Excuse me,
Yeah, Buddha.
we can't see.
Sir,
Okay,
we can't see the
okay. You cannot see, eh? Okay, sorry. Now should be okay. Is it okay now?
yes, sir.
Okay, very good. So this is the energy balance. So when you see this system, you can notice that the mass remains no change. Yeah. So no in, no out. Okay, no in and out. So no in and out means we call this closed system. Okay. Yeah. So this is the first law. I hope you can understand this very well. And this is the energy balance. It is quite easy. Okay, it is quite easy. And there are closed systems. Okay, there are closed systems. So this is a closed system. But there can be other systems. Okay, M no change, but in and out is there. M net no change. There M no change here. M net no change. M net no change. Okay, which means you have in and out possible, and we call this open system. Open system. So in net so you have inlet of mass. Let's say we take one inlet, and also you can have outlet here. Okay, in and out. Okay, you have in and out. So you have in what in mass in. Okay, M in. M in is there. Okay, so let's say the in we take M in this way, and also you have out, M out. So this is what we call the open system. Okay, so here also we have to have the energy balance. Okay, we have to have the energy balance for this as well. So how you are going to do the energy balance? Okay, how we are going to do the energy balance? So here there can be energy in together with M in. Okay, there can be energy in. And also with this M out, there can be energy out. Okay, so you have to consider energy in here with M in, energy out with M out. Okay, so you have to consider this two as well. So energy balance becomes Q in plus W net. Okay, plus energy in with M in. Okay, in with M in plus plus. Okay, so E in with M in. Okay, so you have the, so we will do this way. So as an addition, so E net in with M in minus E out with M out. So you have the net energy E out here, E out. Net energy into the system with mass in and mass out. Net energy E in with M in and minus E out with M out. So you have additional this. Very simple. Additional this. Oh, difficult to read. Yes, E in with M in minus E out with M. So you have the net in of energy Q net plus W net plus this equals delta U is U2 minus U1. I believe this is quite okay for you. Energy balance, first law, for what? Open system. Okay, open systems. Try to understand, and no need to do any noting down or anything. Understanding is very important. When M in is M out, okay, when M in is M out, when M in is M out, we call this flow is steady. Whatever in goes out. Okay. Yeah. So then we call this a steady flow. Okay. When M in is M out, we call the flow is steady. Steady. Okay. Steady. So that is what a steady flow means. Okay. So when the flow is steady, of course it is open system. We can name this as steady flow energy balance. Energy balance. Okay, we call this steady flow energy balance or energy equation. We can say it in a better way. Steady flow energy we call equation instead of balance. Okay, of course this is for. So when you have a steady flow means naturally you should know that it is open system. Steady flow means it is open system. In equals out mass wise. Okay, mass wise in equals out. So steady flow energy we have, of course, based on first law. There is a simple, we call it in the abbreviations SFEE, steady flow energy equation is the first law for open systems. SF. Understand? So this is the SFEE you see down here. SF, steady flow energy equation. Okay. SFEE. Okay. And very nicely we can further simplify this. Okay, let me add a slide. I hope you can understand this very well. So, per unit mass, I use simple E. So here should be times mA. Simple E out times M out is this. Anyway, this is quite okay. Okay, simple M in, E in. Simple E means the energy in per unit mass times E in. E out times M out. Okay, I hope you can understand that. And the same thing, since M in equals M out, I would say this is M. Okay, this is M. So then you can write this as M times E in minus E out. Sorry, I made a little mistake. Let me correct it. Sometimes we can make the mistakes. Here right means, the rise means this one E out with M out should come here, and E in with M in should come here, minus, because it's a rise. No, I think it is okay. Earlier one is okay. Eh? This is okay. It's a rise. Yeah. Good. So E in minus E out. So this is the SFEE. Okay. Yeah. And in the next week, we will try to learn about E in and E out. E in and E out. Memory, I will put this here. Now we have to learn E in and E out. Okay, E in and E out. Because M in here, with E in small n. Okay, M out here with E out. Okay, so the same way, M in for this case, E in per unit mass, and M out, you have E out. E out. Now this capital, so with M in, energy in is big E. With this M out, energy out is big E out. Okay, and if this is not steady, if M in is not M out, if out is more means here the mass is reducing, or if in is more, then the mass in the system will be increasing. Okay, that's why. So I will make it complete because I'm going to email you the slides. Okay, very nice developments. Yeah, good. So the next one is in steady flow energy equations. We have to learn this E in and E out. What is E in? What is E out? Yes. So this one we have to learn. Okay. Then once we learn this, we can apply. This one. So configuring E in and E out. Okay, so this is what we are going to learn afterward. So for this SF, okay, let's see, E, and I get a different this is a bit this. Yes. So E in and E out. So this contains what? Energy types. E in and E out. This contains energy types. Energy types. So let me write down here. You have internal energy, E in and E out, flow in and out with M in and M out with M. So this is what we need to explore. Flow in and out with M. So one component is internal energy. Okay, quite interesting. There should be more. Okay, in and out, in and out. Here we consider not in the system, but in and out. In means you can see in. Here you can see in. Sorry. That. 323. This is in. Okay. In. This is out. So we are focusing on this in and out. Okay, internal energy. In and out. Some bulk kinetic energy. Not the bulk means this is not the molecular level, this is the as a bundle, as a lump of molecules together. So it is out of the individual molecules kinetic energy bulk. So we call bulk or even we call macro or macroscopic. Okay, macro or even we can call macroscopic kinetic energy. Internal energy is micro. Okay, internal energy is micro, molecular, in and out, in and okay. Macro also in and out. You have to look into this. Macro in and out. Okay, bulk in and out, macro in and out, kinetic, and also bulk. There is potential energy in and out. Okay, so we have to look into this as well. Macro kinetic energy, and macro potential energy, and also we have one more at macro level. Flow work. Flow work also turns into energy. Okay, once work, it turns into energy. So we call it flow work in and out. Means to push this to the system, it needs some work. Even moving out, it needs some work. Example, bus එකකට නගිනකොට you need some work. Even get down from the bus. And that is what flow work. Okay, now let's see. It's a simple example. So next week we will be learning this, and this is a very good guide for you if you can study self. Very good. So once we know this, this is for the SFEE systems. Steady flow energy equations we can write. Okay. Yeah. For steady flow energy equations. So starting next week, we will study this. I hope. So this is the last slide. Yeah. So this is the last slide. So the earlier ones. So if I send this to you, maybe better. Do you need this? Hello? Hello?
No, sir.
Huh?
No, sir.
Oh, Buddha. Oh, can you? Oh, දැක්කේ නැද්ද මේවා ටික ඩෙවලොප් කරන්න? Okay? Yeah. Tell me. Anything? Yeah. Anything? Hello?
No, sir.
Ada? Right? Oh, Buddha. Anything? This is about internal energy and SFE. Okay? SFE. We need to develop SFE. You need this?
Yes, sir.
Okay. Of course, I'm going to send this. I just ask only. So let me send it to you all. What is the MAC address, Puta? MAC address 20. What is the mechatronics address? Can you remember? Yeah, BTech Mech 19. Eh? Okay. BTech Mech 19. A second. Can you all understand? Can you all understand?
Yes, yes, sir.
Okay, very good. Because we are going with no any unknown knowledge, all step by step. So I believe you can understand this very well. So I'm sending this now. Hopefully, yeah, message sent. Hopefully you will get it right now. Sambunan Butana. Sambunan. Did you get it?
I will see.
Check.
I
Hasita.
will check, sir.
Okay, check. How the
Yes, sir.
Okay. So you go ahead this one. And with today lessons, even I have these recordings. Maybe later we will look into the recordings as well. So when we are meeting. So how about next week workshop? Workshop technology practicals.
Yes, sir. Sunday, Saturday and Sunday is.
Yes. So this is the last chance. This is the last chance. So we are too late. So Saturday and Sunday somehow we have to do this. If you miss this, you have to make it as a repeat, Puta. Yeah,
Okay.
that's why. So Saturday and Sunday you have to make this with no failures. Okay. So
Okay.
make sure you all are responsible. And next week, so we are canceling the weekend sessions because of this workshop issue. Okay. So we are canceling. So make sure you are there in the VTA. Talk with VTA, Mr. Dilshan, and get it arranged. No more postponements. Yeah. So
Okay.
send us the updates and all, confirm it, and make sure it is done. Okay?
Okay,
Good.
sir.
Good. So that's all from my side today. Any more questions? Anything? I believe it's more clearer to you now. It's more clearer to you now. So the way we are learning seems good. Yeah, seems good. So you are learning all the tips and also bit by bit you are learning. So we have little more to learn. Those are quite easy. So don't worry. Okay, don't worry. So you are really learning. Okay, let me stop the class, Putadin.
Okay,
Okay,
sir.
yeah.
Okay. Thank you, sir.
So thank you very much for joining. Uh, that's all. Okay, Putadin. Okay.